In this lesson, we're going to cover topic 2.6, also known as modeling skills. So usually when we're solving equations, a lot of you don't even know what it means to solve an equation. So sometimes when you have your paper 1 or paper 2, you're given your function. Let's say that your function is x squared plus 2x plus 3 equals 0. And if you're said to solve this function, then what you really have to do is just find the roots. Find the x-intercepts in this case. And these are your answers. And since the first one is squared, you just have two answers, x1 and x2. However, it's a whole lot of different if you have something like x squared plus 2x plus 3 is equal to 5x minus 5. Now this is a lot of different, and if you're told to solve here, you don't want to find the roots of each one. What you have to do is find the intersection of both of them. And that's basically for solving equations. It shouldn't be that hard. It's just when you notice that you have two or more, you just have to find the intersections. So let's go on to solving systems of equations as well. So let's say that you're given that you have your quadratic function, which you should know by now looks something like this. And you're said that it passes these 3 points. The first point is labeled point P, then the letters have no significance, which is 2 and 0. The second point is point L, which is 4 and 8, and the third point is point K, which is 6 and 9. And now you might be wondering, how can I get from all of these points my equation? Well, that's actually very simple. Deconstruct your quadratic function. So you know that 2x squared plus bx plus c is equal to y. And if you take each of these points, you know, let's start with this one, p, 2 and 0. So you clearly know that your first point is the x value and the second point is the y value. And in this case, what you can simply do is just put this point that you have into your function. So you replace all x's and all y's, and then you get something like this, which is a, and then you get something like this, which is a 2 squared plus b times 2 plus c is equal to 0. So if you're still wondering, how do I get these numbers here? The 0 is obviously the y value, therefore it's the y, and all the x's that you have here correspond to the x value that we have here. And then you can simplify it a bit and you get that, you know that 2 squared is 4, so it's 4a plus 2b plus c is equal to 0. And this you have to do for all of this. And then you can simply continue. You will do this as well. So you will get that 4 squared times a, I already switched the paths, plus 4b plus c is equal to 8. Then you also get the third one. Let's use a different color as well. And you can get that 6 squared times a plus 6b plus c is equal to 9. So now you can clearly write out all of your three types of your equations as well, and you can get something like this. So your first one is obviously 4a plus 2b plus c is equal to 0. Then you have 16a plus 4b plus c is equal to 8. Then you have 36a plus 6b is plus c is equal to 9. And if you're still confused where I get these numbers from, the 36, this is obviously 6 squared, this is 4 squared, and this was 2 squared. And you simply take all of these and you enter it here. So you're wondering, okay, what's next? So the next is you obviously use your program. Sadly, my calculator does not have this, but you can go back to my other videos which are topic showed on the screen, and it's obviously linked up there as well, and then you can clearly get your system of equations. Sadly, this calculator, for some reason online, it doesn't have this, so you can just go to my other videos and see how to do this as well. So linear models. So linear models are actually quite simple. So usually you use linear models to actually predict the future, sometimes to predict like what happens in the year, blah 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 blah. And in this case, I think I have brought out a very great example where you have different years and you have the price of Snickers. And in your exercise, you're also told that the price of Snickers is following a linear model. And the question remains that what will the price of Snickers be in 2030? So if you have like boxes and stat like this, you go to stat and edit, and you enter all your information. So 1990, 1995, 2000, 2005, 2010, 2015, 2020, 2025. And then you go enter your prices to L1. So as you can obviously see right here, the first box is obviously all of your X values, and the second plot is all of your Y values. New 63, 71, 85, 92, and 102. So now you most likely have gotten all of your stats entered, and then what you want to do, and then you go to stat and you go to calc, and then you go to linreg. Your X list is all the X values that you have, and the upper ones are usually all of the X values. So your X values are L1, which was the list one. Your Y values are L2. Your frec list is the frequency list, and you only use it when you have actually frequency. We don't have that here. And then you calculate. Or what I recommend you to do is you put store reg ec. And here I recommend you to press vars, you put y vars, you put function, you put y1, and then you calculate. So obviously you have gotten your calculations as well. And then you go to here, and then what you want to do is here in your y value, you want to find the price of Snickers in 2030. Then your maximum X has to be 2030. And then you go to your value and you press your value of X to be 2030. And as you can see here, the price of the Snickers in the year 2030 will be about 1.104. So obviously you can you already should know what the linear model is. It means that the price of Snickers is just going up constantly. And you're checking for the year of 2030, and then you get that your point of the y value, and you know that this is the y value and this is the x value, and the y value is the price, and then you get that y is 1.104. Therefore, in 2030, your Snickers will be 1.104 euros. So, modeling with quadratic functions. I have written out the word optimize. Optimize means that you have to find like the best version. Meaning that sometimes you want to find the maximum, or sometimes you want to find the minimum for some cases. I think the most usual paper 1 and paper 2 exercises using modeling of quadratic functions are like area division. You're given a model. Very usually you're given that the area can be modeled in an quadratic function, meaning that it looks something like this. And this is just a random example. However, you should know by now that if you have a quadratic function that is minus in front, then the tip or the vertex, it looks something like this. And then there is said that find the area with the maximum, find the area where the area is the maximum, and then you obviously have to understand that the y value in this case is the maximum, and then you get that your maximum is in the tip. And you already know from my previous lessons how you can find maximum, it's second trace. I don't want to spend too much time on it because we got a lot to cover in this lesson. So optimizing product design is quite similar. Let's say that you have a billboard, and the billboard can be done in all sorts of different ways. However, you want to find what is the maximum size of the billboard. And then it said that the advertiser wants to get the biggest billboard that they can, and usually it's just given like this. These are not usually quite difficult as well. So fitting data with quadratic functions as well, I think I have even talked about this before. This can be something like waves when your sea level rises and sea level goes back. I wouldn't go into this as much as it's a bit more complicated, and we will definitely learn this in our next lessons as well. So something new as well. So direct variation is actually quite simple. It means that two things are connected with each other. So I really like this one paper 2 exercise where it said basically that the height of the cheetah, let's put y to be height of the cheetah, is connected, and we know that there is some kind of connection with the bear's wave. So we kind of have to understand that it means here that they are connected. And this means that if the height gets bigger, so does get the weight. And this can be also like the proportion can also be to the power, meaning that if you have like, let's use a real life example, that a man's hair length, let's put h as hair length, is proportional to the power of his nose, and then it's clearly written out as something like this. And usually when you're dealing with variation, you're using the word proportional. So for example, the bunny's tail is proportional to the horse's nose, for example. And inverse variation, well, when the direct variation means that if something got bigger, something else also got bigger. Then inverse variation means that if something is getting bigger, then something else is getting smaller. I think we can bring the two examples here as well. So if a man's hair is longer, that means that his nose is usually even smaller. And the M here, always, you might be wondering what the M symbolizes. The M can be a number of like how much. Like if M to be 2 here means that like it's more. And if it's 3, it can be a number that you usually have to calculate out. If we go to direct variation, for example, M here means how big the connection is. Like if the height is like, it can be double the weight. Therefore, if you have double the weight, it's like, it's a connection. So inverse variation is just when something grows, something else decays. So modeling with cubic functions as well. I will not go into this as much depth as well, but you should know that usually when you're asked to use this, it's usually to find the room of the boxes or cups. You can find like the maximum room, the minimum room, and usually I think there are quite easy exercises as well. So modeling with exponential functions is also something that I'm not going to go into much depth as well, as in later on topics I will definitely cover it more. However, you have to know that usually you're dealing with bacteria, as bacteria is something that in the early stages it like grows very slowly. However, the more bacteria that you have, the faster it grows. So the growth is something like this, because you know that one bacteria usually like infects 2 other, and therefore their growth is like exponential. Also something that exponential function usually like covers is depreciation. I wish I could do a small exercises here, but I sadly don't have time. I think depreciation could be like the loss of value of an iPhone, where it first loses a lot of value and then it like slows down, as bad iPhones are still worth something. So modeling with sinusoidal functions. This is the most topic that we're going to cover in this episode. So usually your model looks something like this. Y is equal to A sin bx plus d. So let's get into it. It doesn't have to be C. In many cases you will also cover A cos bx plus d. So let's cover this. So amplitude is A. However, it's not just A. It's the true value of A. Meaning that if your A is negative 2, let's say that you're given that A is negative 2, then the true value of negative 2 is obviously 2, because it's always positive. So the principal axis is the D. Your principal axis is the Y, and the Y is equal to D. So if we have it right here, this is worth. What is the principal axis? So to draw on a little sketch on how it works, usually you have your graph going something like this. I think that's a great graph. So, and then if you kind of start to look at it, you clearly see that you have like the straight line where it's the middle of everything. You don't have that line, but it's more of like an imaginary line. And that line where the length from here is the same of the length to here. So it's exactly in the middle of everything. And that is your Y, also known as D. If you have your Y is A sin B x plus D. Therefore, that is your D. Then also the period. this is the most difficult part, so I will try to cover it the most here as well. So your period is usually worth something like this. So the period is 180 degrees divided by b. Should be, is it should be? No, it's b. So if you want to get the b, for example, you have your equation and you have your a sin bx plus d, and you want to find the b, you should know the rule how to flip things around as well. And then you should know that b is the same as 180 divided by p, and p is the period. And how to find the period to get this as well. So it really depends how it's done. So usually you have your function something like this. Let me draw. Yeah, I think that's great. And then the period you can always find if you look at two maximum spots. So let's look. Let's say that you can find that this is the maximum and here is also maximum. And the period you can always find the maximums. You know, with your GDC second trace, and you got the maximum. You find the points, and then you find their x values. Let's say the first x value is 5 and the second x value is 60. And then if you want to find the period, then you always have to know that period is just you subtract the second point, then it's x2 minus x1, which is in this case 60 minus 5 is equal to 55. And you always have to note that these points have to be one period apart. So if you're confused on what that means, it means that your function has done like a full movement, like from up and down again. And then you can get your b. So in this case, b would be 180 degrees divided by 55. And then you can get, sometimes even b is left out as something like this, but if you want to make sure, you can always do 180 divided by 55. Oh no, 180 divided by 55, and you get your b to be 3.27, which is rounded to 3.27. And of course we will be working with sinusoidal functions even more. However, this can be a very great start. And also something to note here as well, your b isn't always given in degrees, it can be also given in radians. And if it's in radians, you have to know that b is just the period, the b is worth just the period, and here goes 2 pi. And thank you.